In the beginning, we didn't actually know anything about rockets. So our first 3 missions failed, actually, of our Falcon 1 rocket. And we almost ran out of money and just barely made it with the 4th launch. If the 4th launch of Falcon 1 had not succeeded, we would have failed as a company. So we just barely made it. So I have to say that I was not a very good chief engineer in the beginning, but I did learn over time. And I think we've gotten, at this point, to where the vehicle is very reliable. And we are going to be able to take astronauts to Mars. In fact, we want to take anyone who goes to Mars and ultimately build a self-sustaining civilization on Mars. That is the long-term goal of the company.
People often credit SpaceX's founding to Elon Musk's drive, but that alone doesn't convey the intensity and uncertainty of those first years. Picture the year 2001. The future Kubrick imagined hadn't arrived. TRL set the tone of pop culture, and the internet was only beginning to weave itself into daily life. It was in that world that Elon Musk and a handful of engineers decided to attempt something improbable, building a rocket company from scratch. The spark came from Musk's desire to do something visible in space, something concrete enough to nudge the public imagination. He had just left PayPal with enough capital to do nearly anything except the one thing he cared most about, sending something meaningful toward Mars. His first idea, Mars Oasis, was modest by comparison to anything that followed. A small greenhouse on the Martian surface, seeds, moisture, a single fragile living thing taking root in a place no living thing had ever existed. He imagined children seeing that photograph, green life against iron-red dust, and feeling awe rather than apathy. He didn't describe it in promotional language, and he didn't pose it as a breakthrough. It was meant to be symbolic, a demonstration that Mars wasn't beyond reach. What he underestimated at first was how hard it was to simply buy a launch. American rockets were too expensive. The cost of the launch alone would consume the entire budget. So Musk began meeting people in the Mars Society and in the small community of private space advocates trying to understand whether there were unused rockets available anywhere in the world. The answer that kept coming back, quietly, almost conspiratorially, was Russia. After the fall of the Soviet Union, Russian design bureaus still maintained stockpiles of converted ICBMs. They were crude, functional, and theoretically available at prices that sounded impossible by Western standards. Musk recruited aerospace engineer Jim Cantrell to help him navigate the world of ex-Soviet hardware, and took along his old friend Adeo Resi for moral support, though support was not exactly what the trip ended up providing. The first meeting with the Russians had the flavor of a hazing ritual. They were ushered into a room where each participant had a bottle of vodka in front of him, and the toasts began immediately. "To space," someone said. "To cooperation," someone else added. Then, every couple of minutes, another one. "To friendship," "to the mission," "to America," "to Russia." Each toast required another shot. Resi later recalled looking over at Musk and Cantrell, both unconscious on the table. Then he passed out too. The Russians seemed unbothered. This, in their view, was simply the negotiation environment. Over multiple trips, the pattern repeated. They drank, they waited, they endured shifting price quotes and theatrical insults. On the third trip, a chief designer, irritated by Musk's refusal to accept a sudden price hike, spat on his shoes. At another moment, when Musk tried to push back against the escalating costs, a Russian manager sneered at him, "Little boy, you don't have the money." The condescension was almost as disorienting as the vodka. Musk had walked in ready to spend tens of millions, but he left without a rocket, and with the dawning realization that buying one from the Russians might be impossible, no matter how much he offered. On the flight home from Moscow, Cantrell looked over to see Musk absorbed in a spreadsheet. When asked what he was doing, Musk replied almost casually that he was calculating what it would cost to build a rocket, not buy one, build one. The phrase settled strangely into the stale air of the cabin. Aerospace companies did not start this way. They were supposed to emerge from decades of institutional experience, from national laboratories, from military procurement chains. But Musk believed, truly believed, that the cost structure of rockets was artificial, propped up by bureaucracy rather than physics. If materials were inexpensive and engineering talent was underutilized, then why not build a vertically integrated rocket company from the ground up? He incorporated space exploration technologies in May 2002. He put a significant portion of his newly earned wealth into the company, and even then it was a fraction of what traditional aerospace contractors spent annually on overhead alone. He leased a warehouse in El Segundo, near Los Angeles International Airport, an unglamorous, echoing space large enough to set up welding stations, a machine shop, and the embryonic form of a rocket factory. The atmosphere in that building in 2002 and 2003 cannot be understood by looking at photographs of it today. The place smelled of machining oil and aluminum dust. New hires brought their own tools because SpaceX didn't yet have enough. One engineer later recalled that Musk would browse eBay looking for industrial equipment, buying lathes and milling machines the way other people buy used bicycles. The first major technical hire was Tom Mueller, a propulsion engineer who spent his weekends building large liquid fuel engines with an amateur rocketry group. Musk visited one of those desert test firings and watched Mueller's engine roar to life, throwing sand and dust into the air. Seeing someone build a functioning high-performance engine essentially out of personal interest made a powerful impression on him. Mueller, meanwhile, saw in Musk a level of conviction he didn't encounter often. He agreed to join SpaceX, but only after negotiating a salary guarantee in case the company collapsed. He didn't mince words about the risk. Very few people believed a private company of fewer than 10 employees could reach orbit. Alongside Mueller came Chris Thompson for structures, Hans Königsmann for avionics, and later Gwynne Shotwell, whose combination of technical literacy and business intelligence became indispensable. These were not dozens of Stanford interns or a glossy Silicon Valley recruiting class. SpaceX's first employees were a handful of people willing to break from secure aerospace jobs to attempt something that felt, even to them, slightly absurd. The industry veterans they told about the project generally wished them luck, with the same tone one might use for someone entering a doomed expedition. Yet from the beginning, the atmosphere inside the warehouse was not reckless. It was disciplined and intensely focused. They worked long hours, not out of performative culture building, but because nearly every task required invention. They were designing engines, tanks, valves, avionics, software, and ground systems in parallel. Mueller took the lead on Merlin, the first stage engine, drawing on his experience with prior NASA research projects, but rewriting most of the architecture to achieve lower cost and simpler assembly. The team kept the design pressure fed for the second stage, built the thrust structures in-house, and machined components themselves whenever possible. The problem was that testing rocket engines requires space, very loud space. El Segundo offered none. So the team searched for a remote testing site and found an abandoned facility in McGregor, Texas, previously used for rocket research. It came with a retired test stand, essentially a concrete monolith with embedded steel fixtures, capable of restraining a roaring engine. This became the heart of their propulsion program. Transporting engines to McGregor involved a kind of frontier improvisation. Engineers would mount Merlin onto a flatbed trailer, hitch it to a rented pickup, and drive clear across the American Southwest. On arrival in Texas, they would sleep mere hours, then run tests that echoed for miles. During one test fire, Secret Service agents appeared suddenly on site, having detected activity pointing toward President Bush's ranch in nearby Crawford. After a brief halt, SpaceX adjusted their firing vector and resumed. It was not the kind of complication any traditional contractor would have tolerated, but SpaceX adapted constantly. By 2004, the company was preparing its first launch vehicle, Falcon 1. It was a two-stage rocket with a single Merlin engine on the first stage and a small kerosene engine, the Kestrel, on the second. The design had been chosen not for elegance, but for manufacturability. They didn't have the budget for elaborate structural redundancies or for exotic materials. They aimed for simplicity wherever possible, provided they could achieve reliability through testing. Finding a launch site proved nearly as difficult as building the rocket. Vandenberg Air Force Base seemed promising, but scheduling conflicts made it impossible to secure access. A Titan 4 launch was repeatedly delayed, blocking SpaceX's opportunity window. They considered Cape Canaveral too, but the complexity of navigating Eastern Range requirements would have slowed them further. Eventually, they chose Omelek Island, a tiny spit of land in the Kwajalein Atoll, filled with old missile range infrastructure from the Cold War. It was remote enough to be logistically burdensome, but it came with the advantage of a proven range and an equatorial boost. The rocket was shipped by barge across the ocean, and the team followed. Most had never spent meaningful time on a remote island, let alone one functioning as a spaceport. The heat was relentless, the insects were omnipresent, and every tool shipped late or damaged could derail a week of work. They slept in basic shelters, ate at the Army cafeteria, and spent their days under the steel skeleton of a launch mount, tightening bolts and checking wiring. In March 2006, the first Falcon 1 sat upright on the pad. It was slender, almost fragile-looking compared to the heavy-lift rockets of NASA's fleet. Musk, visibly tense, stood with the small group of employees gathered to witness what they had spent 4 years building. When the countdown reached 0 and the rocket leapt off the pad, it was a moment of genuine elation. 30 seconds later, it was over. A fuel leak caused by a corroded aluminum nut ignited a fire around the engine. The vehicle lost control and disintegrated, scattering debris across the island and even punching a hole through a small roof. The payload, TACSAT-1, was lost. What was striking afterward was not the disappointment, though it was profound, but the sober clarity. The team returned to the failure review meeting with data, not excuses. They replaced vulnerable fittings with corrosion-resistant steel. They reran systems analyses. They planned the next flight. Musk didn't lash out. He didn't offer hollow encouragement either. He simply absorbed the blow and moved to the next step. The loss reinforced something the team had already suspected. Nothing about building a rocket company was going to be linear. The second flight in March 2007 came much closer to orbit. The rocket passed through maximum dynamic pressure, reached stage separation, and ignited the second stage engine. But oscillations built up. The guidance system fought them and lost. The engine shut down early, the orbit was not achieved, and the rocket fell back to Earth. It wasn't a catastrophe, but it wasn't success either. The engineers began to feel the psychological weight creeping in. The thought that maybe the industry veterans were right, maybe it wasn't possible to compress decades of aerospace experience into a handful of frantic years. The third flight, in August 2008, carried several small satellites for NASA and the Department of Defense, evidence that despite previous failures, SpaceX had gained enough credibility to win real customers. The launch began smoothly. First stage performance was nominal. But in the fraction of a second after staging, the empty first stage retained a sliver of thrust from leftover fuel. It nudged back into the second stage, colliding with it, dooming the flight. Engineers watching telemetry knew almost instantly what had happened. The disappointment was physical. This was the moment when the company nearly ceased to exist. Money was nearly gone. Musk's other company, Tesla, was itself staggering through a particularly brutal year. There were nights when Musk admitted he woke screaming, believing either venture could collapse at any moment. The glamour people now associate with him simply wasn't present in 2008. He looked gaunt, exhausted, drained of anything except the stubborn refusal to quit. Failure number 3 left SpaceX on the edge of bankruptcy, but Musk gathered the team and told them he wanted to attempt one more launch. There were enough spare parts and half-finished components scattered between El Segundo and McGregor to assemble a fourth Falcon 1. There was no redundancy left, no backup rocket, no cushion, no escape valve. Either the fourth flight would succeed, or SpaceX would be a historical footnote. To make the schedule, they had to get a flight-ready first stage to the island immediately. A military cargo plane became their makeshift transport. During the descent into Kwajalein, engineers noticed the air pressure change, deforming the thin aluminum walls of the rocket's tanks. If the pressure differential grew, the structure could crumple. An engineer climbed into the vehicle mid-flight and cracked open a vent, equalizing the pressure. That sequence, crawling inside a rocket thousands of feet above the Pacific, armed with an ordinary wrench, captured the improvisational reality of SpaceX at that moment. There was no time for committee meetings or procedural manuals. They solved problems because the alternative was failure. On September 28, 2008, Falcon 1 attempted orbit for the fourth time.
5, 4, 3, 2, 1, 0.
We're in stage
We have
1.
liftoff indication. We have liftoff. SpaceX Falcon 1 launch vehicle. Falcon has cleared the tower.
The tension on the island was quiet and total. The countdown reached 0, the vehicle rose, and every milestone that had previously ended in failure now arrived and passed without incident. First stage shutdown, stage separation, second stage ignition, acceleration into vacuum. When orbital velocity was achieved, the room erupted, not into chaos, but into a kind of stunned, palpable release. Some hugged, some cried, some simply stared at the telemetry screens, absorbing the fact that they had done something no private company had ever done. Falcon 1 was in orbit. Musk released a short statement afterward, thanking his team and acknowledging how close the company had come to disappearing. That was the last money we had, he admitted later. Had the fourth launch failed, there was no path forward. What made the moment profound wasn't triumph, but reprieve, survival. Weeks later, yet another critical moment arrived, this time from outside the company. NASA announced the award of a long-term cargo contract to resupply the International Space Station. SpaceX won a contract valued at over $1 billion for future missions using a vehicle that hadn't even been built yet, Falcon 9. The timing was extraordinary. Without that contract, the fourth launch might have been a historical curiosity rather than a turning point. With it, SpaceX had the revenue horizon it needed to hire, expand, and refine its processes. Looking back, the early history of SpaceX reads like the log of an expedition in which every setback forced adaptation rather than retreat. The Russian negotiators who mocked Musk didn't see what Cantrell saw on the flight home, someone who refused to accept the existing price of admission to space. The engineers in El Segundo, working next to used machine tools and hand-built test rigs, didn't fit the mold of a government contractor. The failures in 2006, 2007, and 2008 were not vindications of the industry's cynicism. They were the tuition cost of building something that no private company had ever attempted. What emerged from those early years was not simply a rocket or a contract or a narrow escape from bankruptcy. What emerged was a culture. SpaceX learned to live with technical discomfort, with the constant proximity of failure, with the requirement to solve problems on timelines that made older companies blanch. It learned to treat engineering as an iterative process rather than a static document. It learned that conviction and desperation can coexist, and that sometimes the only path forward is the one no one believes in yet. By the end of 2008, SpaceX had achieved orbit, secured its survival, and demonstrated that private spaceflight could be more than a speculative idea. The company was no longer a warehouse full of improvised equipment and a handful of believers. It was a functioning launch enterprise, battle-scarred, chastened, and newly dangerous to an industry that had not been meaningfully challenged in decades. This is where the next chapter begins, not with the mythology that later built up around SpaceX, but with the simple, stubborn fact of its survival. The company that almost died 3 times in 2 years would soon attempt something far more audacious, scaling from a single-engine, single-satellite launcher to a reusable orbital system capable of reshaping the economics of space entirely. But the DNA of that transformation was already present, crystallized in the furnace of the early years, forged in Russian conference rooms, Texas test stands, and the open sky above a small strip of sand in the Pacific where, on the 4th attempt, a slender rocket finally held its course all the way to orbit. When Falcon 1 finally reached orbit on that September night in 2008, the celebration inside SpaceX was brief but sincere. For years, the team had lived with failure as a constant companion. Now, for the first time, they had something tangible to point to, an object circling Earth that proved they hadn't been delusional. But the relief lasted only days. The company wasn't built to bask in achievements. What most people didn't realize was that while Falcon 1 was still warm from its first success, Falcon 9 was already consuming the company's attention. The victory simply meant they were now permitted to attempt the impossible again. The NASA cargo contract changed everything. It provided not only the financial oxygen the company needed, but also the psychological shift that comes when an institution as conservative as NASA stakes part of its future on you. But contracts don't build rockets, people do. And in the months after the Falcon 1 triumph, SpaceX's key figures emerged not as archetypes, but as deeply human forces, each working at the limits of their capacities.
So you demonstrate that you've been able to do these crazy, insane, absurdly ambitious things in the past. You can continue, pump people up to do it again, and you try to pull apart this seemingly impossible situation and how are we going to design and develop this, and you pull it into smaller pieces, you build a prototype, you test it, you put prototypes, subsystems together, and you test that, and you kind of use a building block approach to reach your goals.
Gwynne Shotwell felt the shift most acutely. SpaceX's survival had always depended on engineering, but its stability depended on her. While Musk pushed technology at unsafe velocities, Shotwell absorbed the heat that would have otherwise vaporized the company. She became the interface between SpaceX and NASA, SpaceX and the Air Force, SpaceX and the skeptical aerospace establishment. The way people described her in those years wasn't with superlatives, but with relief. Engineers said things like, "Thank God Gwynne was there, because she translated chaos into language other humans could understand." Her meetings with NASA officials weren't performances, they were negotiations grounded in competence. She knew the contracts, the milestones, the politics, the expectations, and NASA trusted her because she didn't bluff. There's a story from early 2009 when NASA inspectors walked the floor of Hawthorne, SpaceX's new headquarters in a converted Boeing factory. The visitors expected PowerPoint slides and cautious promises. Instead, they found Shotwell walking them through half-machined Falcon 9 components with grease on her hands from having touched the hardware minutes earlier. She wasn't putting on a show. She simply didn't see a boundary between the business side and the factory floor. To her, credibility wasn't spoken. It was tangible. The engineers respected her for the same reason the bureaucrats did. She never overpromised, but she also never flinched. When tensions inevitably rose between Musk and NASA, it was often Shotwell who anchored the conversation in reality. Where Shotwell mediated the external world, Tom Mueller anchored the internal one. Propulsion was the heart of SpaceX, and Mueller treated it that way, not with romanticism, but with an almost monastic seriousness. Those who worked with him in the Merlin development program talked about his deep, quiet focus. When Musk demanded engine improvements that would normally take a decade, Mueller didn't object philosophically, he objected practically. He would walk into Musk's office with printouts, sketches, manufacturing timelines. He wasn't argumentative, he was precise. He wanted Merlin to be simple because simplicity was reliability, and reliability was the difference between orbital flight and a smoking crater. Mueller grew Merlin from a fragile prototype into a family of engines, 1A, 1C, 1D, each iteration smoothing rough edges, increasing thrust, refining tolerances. His influence wasn't theatrical, it was structural. Many of the company's later triumphs can be traced back to decisions he made in these years. Regeneratively cooled chambers, thrust vector systems that prioritized robustness over elegance, manufacturability standards that allowed engines to be produced at unprecedented speed. While Musk was often portrayed as the force of disruption, Mueller was the force of continuity, the engineer who made sure the rockets actually worked. But propulsion alone doesn't get a vehicle off the pad. That domain belonged to Tim Buzza, a figure who rarely appears in popular retellings, but whose fingerprints are everywhere in the formative years of SpaceX's growth. Buzza had an engineer's disposition and a builder's intuition. He seemed able to shift between blueprints and scaffolding without losing coherence. On the launch pad at Cape Canaveral, he could tell by sound whether a hydraulic system needed attention. In a meeting with NASA, he could quantify risk in a way that didn't sound like optimism or pessimism, only measurement. When SpaceX moved into the old Boeing facility in Hawthorne, it was Buzza who translated the company's improvisational energy into something resembling industrial production. He built processes not to restrict creativity but to enable scale. A young engineer once described watching him walk the factory floor, stopping at a welded seam on a Falcon 9 structure. He ran his hand across it, frowned, and called over the welder, not to reprimand him, but to ask him to explain his technique. The conversation was technical, collaborative, Booza wanted to understand why a choice had been made before deciding whether it needed correction. That combination of curiosity and scrutiny shaped the company's manufacturing culture. After Falcon 1's final flight, one of the most consequential figures in SpaceX's evolution was Hans Koenigsmann. Koenigsmann had been responsible for avionics and systems reliability, but after 2008, he became something like the conscience of the launch program. He didn't have Musk's intensity or Muller's stern calm. Koenigsmann was quiet, analytical, and gentle in a way people didn't expect from someone whose job was to interrogate failure. But that gentleness masked a ruthless precision. If a valve misbehaved or a sensor drifted, he wanted to know not only the cause, but the underlying logic that allowed the error to exist. The engineers trusted him because he never humiliated them, even when mistakes were severe. In a company where external pressure was immense and internal pressure was volcanic, Koenigsmann's style preserved morale. When Falcon 9 underwent its first integrated tests, he sat through the night with teams debugging issues line by line, drilling into telemetry with the patience of someone sorting through archival documents. He believed that most engineering failures were symptoms of deeper misunderstandings. When something went wrong, he didn't blame individuals, he blamed the model. If these were the figures who shaped SpaceX's middle years, there was still the gravitational pull of Musk at the center. His presence in those years wasn't mythic, it was abrasive and clarifying. People didn't remember him as inspirational so much as relentless. He imposed deadlines that offended the aerospace sense of propriety. He overrode objections when he believed engineers were optimizing in the wrong direction. But he also intervened with startling clarity when a team lost perspective. There was a moment during the early development of the Dragon spacecraft when engineers were debating how much redundancy was enough. Traditional aerospace experience dictated extreme redundancy. Musk stopped the meeting and asked a question no one else would have phrased so bluntly. If we add more mass here, how exactly does that help the mission succeed? They argued. He listened. But in the end, he insisted on designing toward the mission profile rather than toward institutional caution. Dragon was central to SpaceX's identity in these years because it was the first vehicle that needed to live up to NASA standards not for launch, but for orbital operations. The pressure was extraordinary. The cargo resupply mission required a spacecraft capable of approaching, navigating around, and eventually berthing with the International Space Station. That meant it had to work in environments no SpaceX hardware had yet experienced. During testing at Hawthorne, engineers would walk past the pressure vessel, wires and hardware blooming from its core like exposed nerves, and feel a combination of awe and terror. They knew this capsule had to behave flawlessly, while monitored by astronauts who had every reason to be skeptical of private sector engineering. Meanwhile, Falcon 9 itself was evolving at a pace that seemed unwise to almost everyone outside SpaceX. The first version of the rocket, with 9 Merlin engines arranged in a 3x3 grid, was designed with simplicity in mind: identical engines, shared parts, modular manufacturing. But implementing that vision required a kind of obsessive discipline. For every change to an engine, a mount, a bay, a pipe, there were cascading effects downstream. The propulsion group worked impossibly long hours to bring Merlin to the performance curves Musk demanded, while the structures team fought to keep mass low enough to satisfy NASA's payload expectations. Almost every decision carried tension, yet something about the internal culture made disagreement productive rather than corrosive. Engineers argued fiercely because they cared fiercely. The first Falcon 9 flight in June 2010 was a pivotal moment, not just because it succeeded, but because of how it succeeded. The launch looked almost uncharacteristically clean. From the firing room at the Cape, engineers watched the vehicle rise, shedding contrails and symmetrical patterns, every engine performing within expected bounds. When the second stage completed its burn and the dummy payload reached orbit, the team seemed almost disbelieving. Falcon 9's debut wasn't a lucky shot, it was validation of thousands of decisions made by teams that had come to trust one another through shared adversity. Later that year, the first Dragon capsule flew, splashing down in the Pacific and making SpaceX the first private company to recover a spacecraft from orbit. That milestone didn't come with cheers so much as quiet, exhausted satisfaction. People had given years of their lives for that moment, and the dominant emotion was not triumph but something closer to relief, an exhalation that felt overdue. Even then, Musk pushed for what many thought was premature reusability. The idea of landing a first-stage booster vertically was something aerospace engineers categorized not as difficult, but as prohibitively improbable. But Musk had already decided that reusability wasn't optional. It was the only path to radically lower launch costs. The internal debates weren't about whether it was desirable, but about how to do it without sacrificing the company's commitments to NASA. Shotwell was forced to navigate that tension at the political level, reassuring NASA that experimental recovery attempts would not jeopardize cargo missions. Koenigsmann and the reliability teams built safeguards into the launch sequencing so early reusability tests couldn't affect primary mission objectives. The first recovery experiments were unglamorous. In 2013, some Falcon 9 boosters performed boostback and re-entry burns, attempting controlled descents into the ocean. Engineers watched their trajectories on screens with the intensity normally reserved for launch phases. They weren't expecting landings, just stability. When a booster descended into heavy seas and broke apart, the team studied the debris patterns like forensic analysts, trying to understand how the structure behaved under unanticipated loads. Meanwhile, the company was growing at a pace that threatened to fracture its culture. The Hawthorne factory expanded from a handful of rooms to an industrial labyrinth. What had once been a tight-knit group who all knew one another by name became a workforce of thousands. Yet the traits forged in the early years persisted: impatience with inefficiency, intolerance for complacency, comfort with discomfort. Younger engineers who joined during the Falcon 9 era inherited processes shaped by Buzza, engines shaped by Muller, safety cultures shaped by Koenigsmann, and organizational resilience shaped by Shotwell. The most consequential moment of this period came in May 2012, when SpaceX became the first private company to send a spacecraft to the International Space Station. The docking of Dragon wasn't just a technical accomplishment, it was an institutional one. NASA, historically distrustful of new entrants, had bet on a company that barely survived its first decade. The scene in Hawthorne that morning felt less like a victory lap and more like a confirmation that the company had crossed a threshold. The people who had come from industry giants, the ones who had left stable careers for the uncertainty of a startup, finally felt themselves standing on the other side of a chasm. In the years that followed, the cadence of launches increased and the company matured. Yet each milestone retained the emotional texture of the people who built it. Musk remained a force of disruption and friction, someone who could inspire or infuriate with equal intensity. Shotwell became the stabilizing field that balanced him, the person NASA called when they wanted answers grounded in reality. Muller's propulsion principles carried forward into every engine variant. Koenigsmann's approach to failure analysis became embedded in the company's DNA. Buzz's framework for manufacturing enabled SpaceX to increase its launch rate without losing coherence. And the engineers who joined in those years found themselves working for an organization that lived in a constant oscillation between the possible and the improbable. By 2014, SpaceX was no longer the fragile experiment that had nearly vanished after 3 failed Falcon 1 launches. It was now the dominant force in commercial launch, with a reliability record NASA trusted and a technical ambition that made other aerospace companies quietly anxious. The people who had carried the company from crisis to credibility weren't legends. They were individuals who had been forced to discover the limits of their own endurance, vision, and craftsmanship. What made this period extraordinary wasn't the scale of the achievement, but the density of human effort concentrated into those 6 years. SpaceX grew not by linear progression, but by continuous reinvention. Each success carried the residue of the failures that preceded it, and each failure contained the seeds of the next innovation. The company that would eventually attempt to land a rocket on its tail, on a barge, in the ocean, was forged not in triumph, but in tension. Built by people whose names rarely appear in headlines, but whose decisions shape the trajectory of a new era in spaceflight. By 2014, SpaceX had become a company that lived between 2 identities. On the surface, it was still the upstart launch provider that had clawed its way to credibility through Falcon 1 and the early Falcon 9 flights. But internally, something far more radical was beginning to take shape, something that made the Falcon program feel quietly and only in certain rooms, like the closing chapter of an era rather than the defining one. The engineers didn't say this out loud. They were too busy launching satellites and meeting NASA milestones. But the sense of an approaching rupture was there, visible in small gestures and overheard fragments, a closed-off lab in Hawthorne, strange methane plumbing diagrams pinned to whiteboards, and Elon Musk's restless habit of showing up unannounced at propulsion meetings with questions that implied the rules had changed. Even before boosters were landing, before the world understood what SpaceX was becoming, Musk had already decided that rockets should not be disposable and that reaching Mars required a wholly different architecture. Propellant mattered, chemistry mattered, methane and liquid oxygen, cleaner burning, higher performing, easier to produce on Mars, had quietly displaced kerosene in the long-term plan. But deciding this was just the beginning. The engine needed to burn methane didn't exist. The type of engine Musk wanted, a full-flow staged combustion cycle, had been attempted only by Soviet engineers and never perfected. It was the kind of problem that made seasoned propulsion experts mutter under their breath.
But the main thing, I've said this a lot, like when I met Elon, he asked me a question that 99.9% of people would say no to. I told him that I was involved in the development of that 650,000 pound thrust rocket engine at TRW, and he asked me, he said, could you build that engine? And I said yes, which, who would say that, right? I can develop a 650,000 pounds thrust booster engine. Like, yeah, I could probably find the team. If we had the money, we could do it. That is optimism, and that's what he saw. That's, that's what you need. And guess what? We can. We developed my team developed a Raptor engine, which is, more sophisticated than that engine. So it was a long, hard road, but you can do it.
Tom Mueller, who had spent more than a decade proving that SpaceX could build engines without the excesses of legacy aerospace, approached the idea with the pragmatic skepticism of someone who understood the difference between ambition and metallurgy. Full flow was elegant in theory, punishing in reality. You ran both propellants through pre-burners. You pushed the chamber pressure into regimes that made turbo machinery feel fragile. You accepted that nearly everything could go wrong at scales that ruined test stands. Yet something in the challenge appealed to him. This wasn't an incremental improvement. This was a chance to build an engine worthy of an interplanetary vehicle. The propulsion team began assembling a small, secretive subgroup of engineers who were comfortable thinking with equations that felt like they'd been printed from another century. In 2014, you could walk through Hawthorne and not know the Raptor project existed unless you worked in the right corner or knew to notice the faint smell of methane that sometimes lingered in a test bay. The bulk of the company was still focused on reusability. The idea that Falcon 9 boosters might one day land upright was still viewed as ambitious, bordering on reckless by the traditional aerospace world. But inside SpaceX, the mood had shifted from possibility to inevitability. Engineers had watched early test attempts hover briefly over the ocean before tipping over. They had studied telemetry curves, adjusting burn sequences the way musicians tune instruments. Reusable rockets required survival through re-entry forces that seemed unreasonable. Engineers joked grimly that they were designing a skyscraper to fall backward into the atmosphere at Mach 6, and then politely asked permission to land. Yet each flight crept closer. One booster touched down intact for a moment before toppling over. Another hit hard enough to fold itself, but the data was improving and no failure was wasted. Meanwhile, Raptor's development unfolded with its own drama. In McGregor, technicians erected new test cells hardened to withstand pressures no Merlin engine had ever approached. One of the early prototype ignitions produced a shockwave that rattled windows in a radius large enough to prompt curious phone calls. An engineer who witnessed the test remembered it not as a controlled firing, but as something primal, the moment when a new species announced itself. The McGregor engineers worked with the kind of intense camaraderie that only emerges when the work is both dangerous and historic. Test failures were violent but educational. Turbopumps shredded themselves. Injector plates ruptured. Flames occasionally shot out in directions unplanned by the laws of geometry. Yet every anomaly gave them data, and SpaceX thrived on data. They'd rebuild by morning, fire again by afternoon, and send revised models to Hawthorne by nightfall. The pace was brutal, and the only people who stayed were those who found meaning in waking up the next day to do it again. While Raptor grew in power, SpaceX's public trajectory accelerated. The first successful Falcon 9 landing in December 2015 didn't shift the company's internal identity, it confirmed it. People in Hawthorne watched the booster descend onto Landing Zone 1 with faces that flickered between disbelief and recognition. One propulsion engineer whispered, "There it is," not referring to the landing itself, but to the future it implied. The booster stood upright, steam curling around its feet. The world saw a triumphant landmark. Inside SpaceX, they saw a tool. Reusability, once a daring research exercise, became operational doctrine. By 2016, booster recoveries were no longer special events. They were expectations. Failure modes were cataloged, studied, resolved. When a Falcon 9 tipped over on the deck of a drone ship because a landing leg didn't lock properly, Koenigsmann treated the incident the way he treated everything, as a signal that something needed to be understood more deeply. The process hardened SpaceX. Reliability was no longer a theoretical goal. It was an everyday responsibility. Falcon Heavy emerged from this atmosphere of technical confidence. Even inside the company, the rocket felt excessive. The loads on the center core were ferocious. The alignment tolerances were unforgiving. 3 boosters, 27 Merlin engines, and a combined thrust that made even veteran aerospace engineers raise their eyebrows. But for all its spectacle, Falcon Heavy was still powered by Merlin. The company had already begun quietly shifting its emotional investment toward the methane engine being tested in Texas. The first Falcon Heavy launch in February 2018 became iconic for reasons that had little to do with engineering. The sight of 2 boosters descending in synchronized arcs and landing side by side felt theatrical, even cosmic. But inside the engineering pit in Hawthorne, the reaction was more grounded. They watched the telemetry streams as if reviewing a well-executed surgical procedure. The excitement came not from the spectacle, but from the knowledge that reusability at this scale meant the economics of launch had permanently changed. Meanwhile, the Starlink program was ramping up quietly but aggressively. In the back corner of the Hawthorne factory, a small team was building satellites like consumer electronics, repetitively, modularly, in quantities that made industry observers uneasy. Traditional satellites were bespoke, fragile, hand-built artifacts. Starlink satellites were closer to appliances, designed to be produced by the dozens. The first test batch in 2018 revealed how much the team still had to learn. Several satellites lost contact, others drifted, thermal and power anomalies emerged, but the constellation had begun. And Falcon 9's reusability meant the cost of deploying satellites dropped dramatically. Engineers joked that they were launching connectivity the same way farmers sowed fields, frequently with the expectation that some wouldn't survive. Starlink was more than a revenue stream. It was a rehearsal for the scale required for a Mars-bound vehicle. Manufacturing thousands of satellites taught SpaceX how to build hardware fast, cheap, and in parallel, a necessary muscle for the future Starship fleet. By 2019, the company's different threads, reusability, Starlink, Falcon Heavy, Crew Dragon, began converging, and Raptor moved from the shadows into the center of the story. After years of testing, the engine was ready to fly. The first Raptor fires in McGregor were events that drew small crowds, not spectators, but engineers who pretended to be passing through. The ignition sequence was different from Merlin's. The sound was deeper, heavier, less a roar and more a pressure wave. People who felt it in their chest described it like a door unlocking inside the future. One technician, after watching a full-duration burn, said quietly, "That is what it takes to leave Earth for good." No one laughed. Raptor was the first piece of hardware built explicitly for an interplanetary transportation system. Everything about it contradicted the aerospace conservatism SpaceX had spent years fighting. It burned methane and oxygen. It used full-flow staged combustion. It aimed for pressures that required metallurgy to behave near its limits. It was, in its design philosophy, as far from Merlin as Falcon 1 had been from the Space Shuttle. Starship's earliest prototypes, the welded-together cylinders standing in the South Texas wind, looked absurd to outsiders. Even some SpaceX employees admitted they weren't sure whether to view the structures as serious engineering or temporary sculptures. But Starship wasn't a continuation of Falcon. It wasn't meant to be familiar. It was meant to be a leap. At Boca Chica, the first static fires of Raptor mounted to small-scale prototypes produced a feeling that even longtime SpaceX employees struggled to describe. Pressure rippled across the tidal flats. The exhaust plume glowed with a color unusual for kerosene engines. The area around the pad looked like a construction site built by people who fully intended to outrun their own mistakes, and maybe that was accurate. In July 2019, Starhopper, a squat, tank-like test vehicle, rose into the air on a single Raptor engine. It drifted sideways, hovered, and landed with a plump metallic thud. The simplicity of the test belied its importance. The world saw a quirky flying water tower. SpaceX engineers saw the first breath of a new class of vehicle. While Raptor matured, Crew Dragon was approaching its own crucible. The successful uncrewed flight to the International Space Station in March 2019 had lifted spirits across the company. It showed that SpaceX could build a human-rated spacecraft that not only flew but integrated seamlessly with NASA systems. Then the explosion happened. In April 2019, during a static fire test at Cape Canaveral, the same capsule that had flown successfully detonated in a flash violent enough to leave nothing intact. When engineers saw the video, the room fell silent. They didn't need explanations to feel the weight of it. The spacecraft was meant for astronauts. Losing it was a reminder, unignorable, of what was at stake. Hans Koenigsmann addressed the company with uncharacteristic heaviness. He explained the cause, a valve failure that triggered a chain reaction. But even as he described it, you could sense his mind running ahead to how to prevent anything like it from happening again. They fixed the design, they rebuilt the systems, they tested everything again and again with a kind of solemn urgency. By the time Crew Dragon prepared for its first crewed launch in May 2020, the company felt both older and sharper. The Falcon era had taught them resilience. The Raptor era was teaching them precision. On launch day, people gathered wherever they could, on staircases, around monitors, at the edge of desks. When the rocket lifted from the pad carrying Bob Behnken and Doug Hurley, it wasn't triumphant so much as steady. The launch felt like a culmination rather than a spectacle. The docking with the International Space Station the next day felt even calmer. The astronauts floated into the station with smiles that seemed both personal and symbolic. SpaceX had matured. By 2020, SpaceX existed in two timescales: the practical, reliable cadence of Falcon missions and the wild, speculative urgency of Raptor and Starship. One world was delivering satellites, astronauts, and cargo. The other was trying to rewrite the relationship between civilization and space. The company didn't resolve the tension, it embodied it. In Hawthorne, the engineers working on Starlink would sometimes hear the distant rumble of a Merlin engine being acceptance tested. In Boca Chica, technicians welding Starship rings by hand would glance at Raptor test data on their phones. In McGregor, Raptor engineers chasing higher chamber pressures would watch Falcon 9 boosters lift off on screens mounted above their workstations. Everything interconnected, everything pointed forward. SpaceX had become many things at once: a launch company, a satellite operator, a builder of crewed spacecraft, a pioneer of reusable rockets, and the world's most aggressive private developer of next-generation propulsion. But beneath all of that, it remained what it had always been: a group of people working at the edge of what they understood, propelled by the belief that the boundary could be moved. By the end of 2020, Raptor engines were firing almost weekly. Starship prototypes were rising into the fog above South Texas. Falcon 9 boosters were landing with the regularity of scheduled flights. Crew Dragon had carried humans safely to orbit, and Starlink satellites had begun to form a shimmering network across the night sky. The company that once fought to reach orbit now fought to redefine it. And the people inside SpaceX, older, sharper, more experienced than when Falcon 1 first climbed into the sky, could feel something unmistakable. When the first year of the new decade began, SpaceX was already living inside two incompatible realities. In one, the Falcon 9 program had matured into a machine of almost monotonous reliability. Boosters returned from space and landed with the practiced calm of experienced skydivers. The recovery team spoke about them like colleagues, not hardware. Mission control screens that once produced adrenaline spikes now produced nods. A launch was no longer an event, it was a cadence. NASA trusted SpaceX with human lives. The Air Force trusted them with national security payloads. Commercial customers booked manifest slots the way airlines book gates. And yet, in the other reality, the company was working in a place where the rules had not yet been written. The South Texas marshland that had once attracted fishermen and birdwatchers had become an improvised frontier town of welders, engineers, technicians, and contractors who arrived with a mixture of curiosity and disbelief. Boca Chica Village, once a quiet stretch of sand and single-story homes, now echoed at night with the metallic groans of cranes swinging steel rings into the air. The horizon glowed from floodlights. The wind smelled of salt, mud, and stainless steel. And rising above it all were structures that didn't look like rockets yet, but like unfinished monuments. The earliest Starship prototypes, Mk-1, SN-1, SN-2, were the kinds of objects that made even SpaceX insiders squint. They looked crude, stitched together from shimmering sheets of steel, like something built by a mid-century sculptor. But the welders saw the intention in them, the way a sculptor sees muscle beneath rough marble. Welders slept in RVs near the pad because the schedule demanded hour-by-hour progress. Teams from Hawthorne rotated through South Texas, carrying laptops coated in dust, reviewing CAD models under shade tents that rattled in the wind. People were building aerospace hardware outdoors, in humidity that made electronics sweat. The propulsion engineers who had grown up with Merlin now found themselves handling something different, heavier, hungrier, more temperamental. Raptor wasn't an engine as much as a new kind of creature. Merlin was disciplined and predictable, a sturdy workhorse that had been refined into elegance. Raptor was feral, chamber pressures that made even senior engineers mutter, "That can't be right." Turbo pumps that needed to survive temperatures that pushed metallurgy toward its breaking point, a full-flow staged combustion cycle so complex that even the Soviet engineers who attempted it decades earlier had only managed prototypes. Yet the Raptor team's mood was not fear, but exhilaration. They were riding into engineering territory that had almost no historical precedent. When the first full-duration Raptor tests roared across McGregor in early 2020, the shockwaves rippled through the ground with a depth that Merlin never produced. Video from those tests circulated quietly among SpaceX staff. The comments were never poetic, never celebratory, just simple acknowledgments of scale. "That's the sound of leaving Earth for real," one propulsion engineer wrote in an internal chat. In Boca Chica, when Starhopper rose for its 150-meter test flight on a single Raptor engine, the locals described it as if a grain silo had developed sentience and decided to fly. It rose slowly, a cylinder balancing its weight on a pillar of methane flame, then drifted sideways and settled down on a concrete pad with an awkward but confident thud. It was not graceful, but it worked. And if a flying steel drum could work, so could the machines to come. The real turning point, the moment when even longtime SpaceX veterans felt their assumptions recalibrate, came with the SN-8 flight in December 2020. SN-8 was tall, silver, and almost theatrical in its unfinished smoothness. It looked more like a vessel from retrofuturism than anything the aerospace world had ever sanctioned. At liftoff, the three Raptor engines lit with a brightness so sharp it whitened the ground. SN-8 climbed with a steadiness that surprised even the people who had calculated its ascent. But the ascent wasn't the point. The point was the belly flop maneuver. As SN-8 crested its apogee and turned horizontal, falling toward Earth with its steel flaps feathering against the air like a skydiver testing their limbs, a kind of collective silence filled mission control. People leaned forward, not blinking. The rocket wasn't supposed to glide. Rockets weren't supposed to act like skydivers. But SN-8 did. It descended in a controlled, deliberate skydive that blended aerodynamics and freefall with an elegance that felt almost unnatural. Then came the final seconds. The engines reignited. The vehicle rotated from horizontal to vertical in a single sweeping motion. For a breath, the impossible seemed possible. And then SN-8 hit the ground too hard. Fire blossomed upward, turning the steel body into a brief, brilliant explosion. No one inside SpaceX interpreted the explosion as failure. They interpreted it as an answer. SN-8 had proved the maneuver could work. It had shown the flap control algorithms were viable, that the rotation was controllable, that the Raptor configuration could meet the demands of transition. The landing burn timing could be fixed. Everything could be fixed. SN-9 flew next. then SN-10, then SN-11. Some crashed on landing, some crumpled. SN-10 succeeded, sort of, landing upright before exploding minutes later when residual fuel ignited. Engineers inspected the debris with calm precision. They took notes. They wrote new checklists. Musk told them not to pause. The iteration cycle accelerated like a heartbeat under stress. But even faster than Starship iteration was the cultural acceleration inside SpaceX. People who had joined during the Falcon 9 era had expected hardship, but not this kind of relentless temporal compression. A single week at Boca Chica could contain the equivalent emotional weight of a year elsewhere. Welders joked about overnight redesigns, not realizing the term had become literal. Some engineers described the experience as living in a time warp, days blurred, nights extended into morning, tasks rewritten before they were finished. Gwen Shotwell visited South Texas regularly, and her presence changed the temperature of the room. She walked the construction zones in hard hats, not for show, but because she wanted to understand the obstacles firsthand. When regulatory conflicts arose, when local officials questioned flight schedules, when supply chains bent under the pace, she became the negotiator who translated chaos into actionable language. She had a way of grounding the madness, reminding teams that the future being built on that wet, wind-beaten ground still needed contracts, permissions, clearances, safety, continuity. Meanwhile, Hans Königsmann, the quiet anchor of reliability within SpaceX, confronted the Starship program with a mixture of admiration and professional alarm. He respected the vision, but the pace contradicted every principle of incremental safety he'd spent his career refining. He would examine failure reports with a gravity that reminded younger engineers that explosions might be informative but were never trivial. When he eventually retired, senior staff described it as a profound passing of an era. SpaceX's move from Falcon culture to Starship culture marked not just a technical shift, but a generational one. And it was around this time that Musk introduced the idea that made even Starship engineers blink. The booster would not land on legs. It would be caught. The first time he said it in a meeting, people laughed, carefully, the way one laughs at a joke whose seriousness is not yet known. "We're going to catch the booster," he repeated, and this time no one laughed. The silence became heavy. Musk outlined the reasoning. The booster would return from re-entry guided by its grid fins, align itself with a launch tower equipped with giant mechanical arms, and allow itself to be caught like a falling tree trunk being intercepted mid-air. No legs, no wasted mass, no need for landing pads. A nervous murmur spread among the engineers. One of them later recounted the moment by saying, "He was asking us to intercept a skyscraper moving sideways." But Musk didn't present it as an experiment. He presented it as the plan. The idea wasn't madness. It was just far enough beyond the edge of plausibility that engineering reality would need to stretch to meet it. The tower, later nicknamed Mechazilla, you could build. You could model the grid fin aerodynamics. You could calculate the deceleration windows. But the tolerances were unforgiving. The booster had to return through re-entry precisely, hitting aerodynamic angles that balanced aerodynamic drag against structural survivability. It had to remain stable through supersonic turbulence that punished even millisecond deviations. It had to light engines during descent not to land, but to slow just enough to allow the chopsticks to close around it. A landing burn could be messy. A catch could not. In Hawthorne, simulation teams worked through grid fin vectors and atmospheric models late into the night. In McGregor, Raptor reliability mattered more than ever. Every second of booster control during descent depended on consistent ignition behavior. Engineers couldn't afford combustion instability, throttle lag, or injector oscillations. They chased down chamber pressure anomalies at 2 a.m., running diagnostics while lightning from Gulf storms flashed across the sky outside. The first attempts weren't catches, they were rehearsals. Booster 4 falling cleanly through its descent corridor, Booster 7 flipping engines on for a few moments before falling back to the ocean, Booster 9 demonstrating precision that surprised even its skeptics. Engineers would gather around screens, watching grid fin telemetry with the same tension one watches a surgeon's hands. When the world saw booster re-entries streaking across the sky, glowing as atmospheric friction ignited a halo around them, most people saw beauty. SpaceX engineers saw data, pitch drift, yaw oscillation, thermal margins on grid fins glowing red hot. Starlink expanded during these years from an engineering project into a geopolitical force. As thousands of satellites launched aboard reused Falcon 9 boosters, the constellation became impossible for governments to ignore. Rural communities used it for basic communication, researchers used it in remote field sites, and then wars used it. In Ukraine, field commanders depended on Starlink terminals for coordination and intelligence. Defense officials saw it as the kind of asset nations use to control, not corporations. In private, government staffers would admit to an unsettling truth. They depended on a private company for orbital access and global communications infrastructure. Some felt relief, some felt unease. All understood that the balance of power between states and corporations had shifted quietly but decisively. SpaceX became indispensable to NASA as well. When the agency selected Starship as the lander for the Artemis moon mission, half the organization greeted the announcement with excitement, and the other half with something close to dread. Starship was powerful, potentially revolutionary, but unproven. During internal NASA reviews, senior engineers argued over whether SpaceX's iteration pace was a strength or a liability. They'll move faster than we can regulate, one worried, and maybe faster than we can support. Back at Boca Chica, the ground shook beneath the construction cranes as super-heavy prototypes fired more Raptors than any engine cluster had ever contained. A kind of collective seriousness settled over the Starship teams. They were no longer building prototypes for atmospheric tests. They were building a system NASA wanted to send people to the lunar surface. And they were building the architecture Musk wanted to send people to Mars. The first full-stack flights of Starship and Super Heavy were thunderous lessons. Engines failed, tanks buckled, booster separation events tore themselves apart in midair, but each attempt cut new grooves of understanding into the engineering teams. One flight returned data that prompted Musk to walk the site in silence for several minutes before telling the team, "Good, now we know." He wasn't dismissing the failure, he was accepting the tuition price for learning. By 2024, catching a booster was no longer a joke, nor a theory. It became the next test milestone, one that made even hardened SpaceX engineers feel anxious. The tower arms, the chopsticks, looked delicate compared to the steel mass they were meant to absorb. Technicians had rehearsed the movement hundreds of times. Software teams had tuned the control algorithms with the precision of neurosurgeons. Everything depended on timing within inches, milliseconds. On a humid South Texas morning in 2025, with cranes paused and welders watching from wherever they could find vantage, a super heavy booster fell through the sky with a quiet confidence. The grid fins glowed, the booster held alignment, telemetry streamed, the engines lit for their final burn, not to land, but to slow. The chopsticks opened. The booster sank into their cradle like an enormous pendulum finding equilibrium. Steel met steel with a muted, resonant thrum. Dust rose. Someone exhaled. Someone laughed, but covered their mouth in disbelief. The tower held. The booster hung there, still smoking, alive. People stood frozen. A few cried, not from sentimentality, but from the realization that they had crossed into territory aerospace history had never charted. A rocket had returned from re-entry, from the edge of space, and been caught by a machine built by human hands. Later, when the official press photos circulated, commentators reached for metaphors. But in Boca Chica, people remembered the sound, the quietness of it, the way the arms absorbed the mass with a softness that felt out of proportion to the forces involved. A machine catching a machine, precision catching momentum. After the catch, SpaceX engineers gathered around the base of the tower in the late afternoon light. Someone asked what came next. Someone else said, "Now we do it again." And that was that. By 2025, SpaceX existed as a paradox. A company that felt both impossibly large and impossibly young, both indispensable to global infrastructure and still experimenting on the edge of physical possibility. Governments depended on it, NASA depended on it, militaries watched it, diplomats negotiated around it, regulators attempted to absorb the implications of a launch cadence that made policy cycles feel geological. Inside Hawthorne and Boca Chica, the atmosphere was quieter than the world imagined. People worked, people argued, people revised CAD models and tightened bolts and rewrote lines of code late into the night. The ambition was enormous, but the tasks were grounded. The future was not a dream, it was a list. Starship was no longer a prototype. Raptor was no longer a test article. Starlink was no longer an experiment. The Mechazilla catch was no longer a theory. SpaceX had entered a new stage, one where the company's capabilities were beginning to exceed the vocabulary available to describe them. A private organization had achieved something once reserved for superpowers: complete end-to-end mastery of launch, landing, communications, and propulsion at a scale unmatched by any nation. But inside SpaceX, the mood was simpler. Pride, yes, but also unease. The engineers understood the weight resting on their shoulders. The civilization-level implications weren't abstractions to them. They felt them in the vibrations of each test firing, the stress traces across each Raptor turbo pump, the shockwaves rolling across coastal wetlands each time a vehicle rose and fell again. The story of SpaceX in these years wasn't simply technological, it was human. The welders who shaped steel rings in the dark, the propulsion engineers who chased chamber pressures that seemed to defy metallurgy, the managers who tried to impose order on chaos without extinguishing the fire that made it possible, the leaders who navigated between inspiration and exhaustion, the cultures that formed inside tents, trailers, and unmarked conference rooms, the small triumphs, the heavy silences, the way people leaned on each other when something exploded that shouldn't have, the way they lifted each other when something worked that had no right to. Starship rose, Super Heavy returned, a tower caught a rocket, and the people who made it possible stood there beneath a sky streaked with the condensation trails of things that once existed only as sketches, wondering, quietly, privately, what it meant that they were the ones building the future. Because by 2025, the question was no longer whether SpaceX could deliver the future. By 2025, the world had grown used to seeing rockets land, but not to understanding what it meant. Even officials who spent their careers analyzing military balance watched boosters descend in silence, trying to grasp the implications. For decades, launch capacity had been a measure of national strength. Now a private company in California and South Texas launched more mass to orbit than most countries combined. It wasn't a sudden shift, but it was irreversible. Inside the U.S. government, discussions about SpaceX had moved from technical assessments to strategic calculations. Reusable rockets weren't just cheaper, they were responsive. A fleet of boosters that could fly, land, refuel, and fly again altered logistics, satellite deployment, and deterrence itself. Agencies that once planned in decades now realized a private company could redesign its hardware faster than they could update a budget line. NASA felt the shift as well. Without Falcon 9 and Crew Dragon, the United States would still be reliant on foreign vehicles for human spaceflight. Without Starship, the Artemis program's ambitions would be distant abstractions. Many inside NASA admired SpaceX's velocity. Others were unsettled by it. The dependence was real. If SpaceX faltered, the national space program would falter with it. Starlink heightened this dependence. What began as a technology experiment had become global infrastructure, used by farmers, field researchers, disaster responders, and militaries. Governments found themselves reliant on a communications system they did not control. European regulators debated sovereignty. American officials debated contingency plans. Some allies viewed it as a gift. Others viewed it as a strategic vulnerability. Yet in South Texas, none of this mattered day to day. On the ground, the work was local, physical, immediate. Weld seams that needed reinforcing, Raptor engines that needed taming, grid fins that needed rethinking, software that needed rewriting at 3 a.m. SpaceX lived in the details, even as the consequences of those details reached far beyond the marshes and cranes of Boca Chica. The early Starship prototypes, towering silver cylinders stitched together by welders working in wind and salt, didn't look like the foundation of a new era. They looked improvised. But the teams building them treated the work with a seriousness that bordered on devotion. Many lived out of RVs, working shifts that blurred into each other. They were building aerospace hardware outdoors, in humidity that fogged their screens and sweat that stung their eyes. Raptor changed the tone even more. Merlin had been a disciplined workhorse. Raptor was an animal. Full-flow staged combustion, extreme chamber pressures, turbo machinery that demanded metallurgical perfection. This was propulsion at the edge of what was possible. The first full-duration tests at McGregor shook the ground with a depth that left even veteran engineers quiet afterward. They weren't watching an engine, they were watching a gateway. When Starhopper rose awkwardly into the air in 2019 and settled back onto its pad, the engineers didn't cheer for the spectacle. They cheered because it meant the math was right. The leap came with SN8. Watching it belly flop in controlled freefall, its flaps actuating like limbs of a creature learning how to fly sideways, engineers in mission control held their breath. The flip maneuver in the final seconds felt like an act of defiance against the laws of motion. The explosion on landing felt almost irrelevant. SN8 had shown that Starship could move through the sky the way it needed to. SN9, SN10, SN11 each taught something. Some landed and collapsed. Some never reached the pad. Each failure was both a loss and a dataset. SpaceX didn't stall. The teams absorbed lessons and moved on, faster than most observers believed responsible, but never without review, never without reflection. Then came the moment that seemed to redefine the boundary between ambition and physics. Musk's statement that the booster would not land, but be caught. At first, engineers thought he was joking. Then they realized he wasn't. The idea was simple to describe, nearly impossible to execute. Guide a skyscraper-sized booster through re-entry turbulence and into the arms of a launch tower. No legs, no landing pad, just precision. Skepticism was quiet, but universal. A few murmured, "You want us to intercept a building?" But they didn't refuse. They modeled the descent profile, redesigned grid fins, hardened avionics systems, and taught the Raptor engines to throttle fast enough for micro-adjustments. Starlink deployments accelerated. Thousands of satellites transformed into a shimmering mesh around Earth. Militaries used it. Emergency responders used it. Refugees used it. A communications network built originally to fund a Mars rocket had become something geopolitical in its own right. Nations debated regulation. Diplomats debated leverage. The strategic questions multiplied. And then, in 2025, a super heavy booster fell through the sky exactly as planned. The chopsticks opened, engines pulsed. The booster slid into the cradle, a titanic object settling into the arms of a machine built for a future few dared articulate. The impact was controlled, muted, almost gentle. A rocket returning from space had been caught. Some engineers cried, others laughed in disbelief. Most simply stared, exhausted and proud in a way that no speech could summarize. The catch was not the end of a journey, it was the beginning of a new one. By then, SpaceX wasn't just a launch provider, it was infrastructure. Nations counted on it, NASA depended on it, the Pentagon strategized around it, regulators struggled to keep pace with it. Some called this exciting, others called it unnerving. Both were right. Inside the company, the atmosphere was less dramatic. People were busy. They solved problems no one outside the building would ever know existed. They fought fatigue. They carried not just ambition, but responsibility. They had built a system that expanded the reach of civilization, and they felt the weight of that quietly, privately. When welders looked at a Starship ring glowing red in the dark, they didn't think about geopolitics. When Raptor engineers diagnosed pump cavitation at midnight, they didn't think about Artemis timelines. When flight controllers argued over tuning a descent algorithm, they didn't think about deterrence theory. They thought about the problem in front of them. Meaning, for them, came from precision, not from speeches, but occasionally, usually in the early morning before the pads came alive, some engineers would walk the perimeter and look up at the silhouettes rising above the marsh. They would stand in the wind, listening to the distant hum of generators, and feel something fundamental, not triumph, not fear, responsibility, and a kind of sober inspiration born from the knowledge that the work mattered and that none of it was guaranteed. SpaceX had changed the industry, it had changed national strategy, it had changed the timeline of space exploration, but inside the company, the people who built Starship understood a truth far too grounded to be captured in headlines. Technological revolutions are fragile. They demand vigilance. They demand humility. They demand people willing to carry both ambition and doubt in the same breath. By 2025, SpaceX had become one of the central pillars of modern civilization, not through rhetoric, but through results. The company's achievements were monumental, but the people behind them worked one weld, one engine, one line of code at a time. They had shifted the trajectory of the world, not by dreaming bigger, but by building relentlessly. Konstantin Tsiolkovsky once noted, "Earth is the cradle of humanity, but one cannot remain in the cradle forever." In South Texas and Hawthorne, the engineers at SpaceX are quietly carrying out the work required to lift us beyond that cradle.
That's been the goal of SpaceX from the beginning, from 2002. And here we are 23 years later. So it's a long journey. And with a super talent, like by far, I think the most talented group of rocket engineers that's ever been assembled. And we're finally, next year, I think we'll be able to achieve full reusability.